Okay. Okay. So we are continuing our way through sheet 33 examples, and we're at onto one of the final sections of chapter 4. Chapter 4 being on topology introduces a lot of key material for the concept of sheaves, because as Rosiak notes, sheaves really combine the notion of a topology with these notions associated with pre-sheaves. And we've been learning many concepts regarding topologies, their definition at a more abstract level. We also spent a lot of time last time talking about closed sets, limit points, and notions that really come to the fore when we're dealing with not finite sets, but infinite sets, right? And for this time, we're talking about a concept that is very, very important for sheaves in particular, even more centrally than for pre-sheaves, which is the concept of a cover. And once again, here, as last time, a lot of the concepts are more subtle when we're dealing with infinite sets. We're dealing with finite sets, for example, this notion that comes up in this subsection 4.3.2, notion of compactness. All finite sets are compact, but not all infinite sets are compact. Compactness is a very special property for infinite sets. And we are going to be discussing some of these concepts that are rather particular for infinite sets, and some of them which are more foundational in the sense that we have to think about them as well for even finite sets, fairly hard. Okay, so with that sort of basic opening set of remarks, I'll switch over to the slides here. So I'm going to talk about covers. One of the final things in this subsection, and one of the final things in my remarks today, will be on covers as sort of helping us bring in the topic of introducing combinatorial representations with simplicial complexes. And we'll talk, as does the subsection, about the nerve of a cover, and how we can characterize it with an abstract simplicial concept, complex. Okay, so as I think you folks should all have encountered, the notion of a cover is a notion that comes up with sets, right? So if we have a topological space X and we have some subset within them, remember the topological space includes a set, right? And really, to be fulsome in the treatment, there should really be X comma tau, where tau is the collection of open sets, for example, of the topological space, right? Each of which is a subset of X. Remember that? Such that they're closed under finite intersection, an arbitrary union, and X and the empty set are also in tau. As Rosiak notes, it's often just when that's implied, or when we don't need to talk about delta explicitly, we just say X. But you should be aware it's X with some topology, delta, or sorry, tau. Some topology, we'll call it tau. Okay, so a subset of this topological space, if we have a subset, a cover of it is a collection of subsets of X. In other words, some subset of the power set of X, right? The power set of X is all these different subsets of X, and a cover is some subset of that, some particular elements of this power set, some particular subsets of X, such that they cover S in the sense that if you union together those subsets in the cover, if you union them together, they include S, right? Note that they may include some things beyond S, right? Like they may have some things that stick out of S, like that aren't limited to S. That's fine, but we need to cover S with them, right? And so we have this the cover in the topological space X is some collection of subsets of X such that when we union them together, they include S, right? The thing we want to cover. Now, an open cover of some subset X of a topological space is again some where this subset is a subset of X, right? Of the total set is a collection of open subsets, these open sets, right, of the topology, such that when we union them together, we cover S. So this will be for open cover drawn from the open sets of the topology, right? And as Rosiak notes, like in our last discussion, he had noted there's this duality between closed covers and open cover, or sorry, between closed sets and open sets. And we can define similar things with closed covers. It's not that open covers are terribly privileged, just that it's a more common treatment. Okay, so a few examples of this, right? For topological space X and tau. X itself is an open cover of X. Does that make sense? Like, remember the cover is a collection of subsets of the total. This is one subset of the total, and this is a collection of them, just that one. And that itself is sufficient to cover itself, right? In kind of a trivial way. It's the coarsest cover. It has no fine-grained components, right? But commonly we want to be more thoughtful or more discriminating than that in terms of what we use to cover it. And in general, the cover might be a set of many different subsets of X that collectively come together to form X, right? So tempted to start on these examples here, but before we get to these infinite examples, maybe we will do just a sanity check on the board here, right? So we have these from last time, and I put them in the slides from last time, so we can erase them. Okay, so I'm going to for reasons that may seem obvious, I'm going to may not be obvious right now, but will soon be evident. I'm going to start writing sets like this, and we're going to start dealing with bundles, which sort of each of these is associated with some data above it, so it'll be a useful diagrammatic mechanism. But I'm going to write down, this is our set here. I'm going to write down some things. You're going to tell me whether they're covers of it, right? Okay, so if I wrote down, A, B, E, and B, C, and A, D, C, would that be And would that be a cover of this? What are we looking for? Whether each of these can be found in at least one of these sets, right? So A, check, B, check, C, yeah, check, D, check, E, check, right? You notice there's a lot of overlap, like A is in 2, B is in 2, right? But C is in 2 of them, but that's fine, right? What if we had A, C, and B? Was that a cover? Why not? Sorry?
Doesn't cover E and
Doesn't cover E and D, right? Good. Good. What if we had A, B, C, D, E, and you know, A, D? Is that a cover? Yeah, it's a cover, right? And what this is talking about, what we just said, is like the set consisting of just this set by itself is kind of the coarsest cover. What would a fine cover be for this? What would a really fine cover be? Define in sense of fine grain, not like what a fine thing. What would a fine one be?
one that comes to mind is just the power set.
Okay, well, a power set would include, yeah, the power set would have all subsets, but what's fairly small, fairly compact, and but I'll give you a hint, it only has 5 elements in it. Well, I mean, A, B, C, D. My brackets are really suffering here. Curly bracket. Are really suffering, eh? Curly brace. What's that?
Looks like pasta.
Yeah. That's right. That's right. Sort of Italian style pasta, kind of. So this would be a very fine grained one, right? Now, these examples, although I just pulled them out of my head, I mean, they include, they presage some of the concepts we'll be talking about, right? Like some of these admit subcovers, right? Which is one here that might admit a subcover? So it includes, it is a cover, but it also has a subcover, a sort of subset of the sets that could still cover it.
The first one, because that first set is ABE, and the last one is ABC.
Yes,
And that's all that's missing.
I think E is missing.
No, E is in the first subset.
Okay, sorry. So you're saying this one and
the third set.
D.
Well, yeah, ABE and ADC.
Oh, ABE and ADC. Yeah. Sorry. Yeah. That's right. That's right. Good. So that admits this. Is there any other that admits a subcover? Well, this one, like this one is kind of a subcover. But there's also a notion of granularity that you're seeing here, like this notion of refinement comes in, where like this one has finer grain sets than this one, for example. They both cover it, but this does so with a finer level of resolution, right? And it turns out that that's really important for sheets. Having this extra resolution and your open cover. Okay, so back to the salt mines, back to the slides here. So for so these are some finite examples, and as we see, it's a rather pleasingly, sort of refreshingly simple notion for finite sets. I would notion I could also draw rather than turning the curly braces into spaghetti, or no, it's not spaghetti, it's more like, I don't know, rotini or something. I could have like drawn arcs around like geometric figures that include some of it, like, right? I could have had like a little region that included A, B, and D or something by looping around, and I could actually show the sets as these geometric images, and there you'd actually see overlapping very visually. You'd see overlapping between them, but eventually it would get a little bit cumbersome because there'd be so many overlapping things. You might run out of colors. Okay. So let's talk about these for some continuous sets. So for the usual topology, you'll remember that associated with, remember we talked about it with open balls and so on, and for Rn. Here we have or here it would be open, disks or open intervals, right? And their union between them constituting the open sets. So for the reals, single real, it's covered by this cover. Why does that cover it? Can anyone say? Like, does n, and so here is it, n is an integer. Why does this cover the reals if n is just a puny integer, just a scrawny integer? Why does it cover the reals?
The only potential excluded elements would be the integer elements themselves because they're at the edges of the cover intervals, but each interval includes n+1.
That's right.
And so
That's right. So it includes the middle one. And because this is done for every integer, not just for the even ones or something, you go and you have successive coverage of every integer, but more than that, you cover all the things other than the integers too, right? Good. This is a nested cover, right? So like you could think of it going out. That's kind of weird. This could actually be from natural numbers. I don't know why it has to be from, I mean, it could be from reals, but it could also be, or sorry, from integers, but it could be for natural numbers, right? Successively larger ones, and they're nested. They're kind of like towers of Hanoi, these little disks that grow. They're on top of each other, right? And it is a cover for the reals because this is arbitrarily large, and it goes from n to minus n. It covers all the reals in there. It's open on the two sides. Okay. So I think you're comfortable with that. Okay, now subcovers. I started introducing them there. So this is an important notion, and so one cover set. So in a subcover consists of a cover set whose collection of open sets. The collection is a subset of the collection of the open sets of another open cover of the same. I put in open. I mean, this should really say open here because it doesn't always apply for open, but a lot of the time I think we'll be reasonable about it for open. So the point here is, though, that the distinguishing thing about the subcover is that it has a subset. The collection of sets for the subcover, or subsets for the subcover, that collection is itself a subset of the other collection. It isn't that necessarily the sets within the collection are thinner. No. It's like the collection is a subset. It has just includes some of the subsets featured in the broader set, right? It's selective. It selects certain ones out. That's the distinguishing feature, not that it uses more refined, smaller sets within the collection. No, it's that the collection is a collection of selected ones from the broader collection. And yet it covers, right? It covers, so it's a cover for the same set. So here's the thing we want to cover, 0 to 1, open. And this is a cover for it, but this is a subcover of that, right? And I colored them just to make it clear, like we took this one and we took this one. These are the same sets as over here, but these are a subset of these, right? Make sense? And this covers 0, 1, right? There's some overlap between this and this by about a half, but it covers 0, 1, the open interval between 0 and 1. Are we good with that? Okay. And one thing that Rosiak talks about is that you can have open covers that do not have subcovers. You can have covers that do not have subcovers. So he introduces this one for covering the reals. This open cover has no non-trivial subcovers. So let's think about this. Okay, there's something going on here. This should be the union of all these U's, right? Excuse me. No, this is a set of U's, and we're dealing with the set. The cover is the set UN like this, right? This is the cover, right? So cover consists of these sets. So why does it have no non-trivial subcovers?
This set doesn't have any intersection.
That's right. Well, it does not intersect at the ends, but it covers the middle one, which is what Jeff was saying before. It doesn't cover it at the ends. And so if you knocked out any one of these, what would happen?
The integer in the middle of the
integer in the middle would no longer be covered. And therefore, you wouldn't cover all of the reals. So it's very sensitive to knocking even one of these out. At first glance, it may seem wasteful, like, wait a minute, you're needlessly overlapping, right, at the ends. After all, there's a bunch that's going to overlap each time with the neighbors to the left and the right, so to speak, right? But it's designed such that, well, I mean, if you knock out any of these, you might think you're saving overlap, but no. You're actually knocking out one of the key things, which is covering well, I think of it as key, an integer in the middle, right? Which would otherwise not be covered, I think is what Mehdi was saying. It's not covered at either end, right? Okay, finite subcovers. So we're talking about subcovers. Let's talk about finite subcovers. So a finite subcover is a subcover consisting of a finite number of sets, not of sets that are themselves finite. No, it's a finite number of sets, right? Okay. So if we have let me ask this. If we have a finite set, like 5 elements, like this one, or 150,000 elements, does it always have a finite cover? Yes. Yeah. I mean, the finest one, right? Like even as Jeff said, even the discrete, well, so even the power set would cover it. Very wastefully, but it would be finite. So yes, it is finite cover. And bikes, and if it were the power set, well, that would have a finite subcover because there's the whole set in there, and then there's all the pieces of that whole set individually, even, and so there's a finite subcover. So for finite sets, this isn't as interesting, right? I mean, we still have subcovers for finite sets. We still have covers for finite sets. But they're more straightforward. Maybe you'd say they're less subtle. But now we're talking, okay, infinite sets, maybe like the interval between 0 and 1. As an example, infinite sets are infinitely many points there. Do we have, if we have a cover of that, do we have a finite subcover, something, a subset of that cover? Subset, so a subcollection of those sets for the cover, which still cover the entire infinite number of points between 0 and 1 open, right? So Rosiak notes not every cover has a finite subcover, right? Here we were just talking about old covers, right? We were saying like this doesn't have a subcover at all, right? Remember this? We knock even one of these out, the result would still be infinite, but it still wouldn't cover this. Now we're talking something more aggressive. Is there a subcover that's finite? There's a finite number of sets in it, right? Okay, so let's talk about this. Okay, define UN to be the open interval from minus n over 3 to n over 3. Okay. And then we consider as our cover, we'll talk about subcovers, we're going to first talk about our cover as the union of all these things for all, n being all natural numbers. We comfortable with this notion? Okay, so we have, n being 0. This goes an open interval, right, from 0 to 0. It's really nothing. The empty set, and then for n equals 1 from minus 1/3 to 1/3, right? And you're unioning them all together. Okay, that's a lot of overlap there, but yeah, fine. And the claim is, oh, wait a minute. I should have said, like, what are we, okay, why didn't I say this? Each of these, so here we're trying to cover, I don't know why I didn't say this. Example, cover 0, 1, right? We're trying to cover this subset, right? I mean, for a cover, we need to say what set S we're trying to cover, right? So I'm saying S here is this, right? Okay. Okay. And I might as well, just because I think the same bug came up below and how I wrote this down. Okay. Here. There we go. Sorry. Okay. So we're going to cover this. We want to cover this. And we have this, and we take the union. First of all, does that cover this? Does that cover this? If we take the union of all these for n drawn from the natural numbers, does it cover that? Yeah, it covers it. But it actually, does it have a finite subcover? Yes. What's the finite subcover of it? What subset of these sets UN will cover 0, 1.
Could just use the first three.
The first three. Or even, like, I think just U3.
Right.
Do I have a bug in my thinking? Right? U3 itself goes from -1 open to 1 open. Right? So that will work. That will cover it, right? We're comfortable with that? Okay. This one has a finite subcover, right? This is a finite subcover. Why is it finite? Because what? There's just 3. It's finite set. Right. Okay. Again, it's not that the U's themselves are finite. No, it's that there's a finite set of these U's, right? It so happens the U's are finite, but that's not really germane to whether it's a finite subcover. These are a subcover of this because they're a sub-collection of these, right? Okay. Okay, this is kind of a funky example. Well, it's funky for me as a computer scientist or something. Okay, so it goes from -infinity to -1 closed there, -infinity open. Union of this from 1 closed to infinity open. Okay, so it's kind of this. It's kind of thing with this gap in the center between -1 and 1 open, right? There's this kind of gap from -1 to 1 open on both sides, which is not within the set to cover. And the remark from Rosiak is, these are from Rosiak, right? The remark is, this has open cover. -1. So consists of sets for all integers from n-1 to n+2. So there'll be sort of successive kind of windows, right? Do these windows overlap for successive n?
Yes.
Yeah, they overlap. There's actually a lot of overlap, right? Because they're of length, well, 3, but open on both sides, right? Okay, so they overlap, but they cover things because they're of length 3. Even though they're open on the side, they cover everything in the middle, right? Okay, that's kind of cool. So does this cover this entire span? It does. It does. But then the question is, does it have a finite subcover that covers S? No.
If you remove any of them, it won't cover. For example, remove
That's right.
larger part, then the infinity part won't be covered.
Right. Right. So could we like knock out every other one, for example? What would happen if we knocked out every other one? Okay, so just think about it. Let's say n equals 0. Let's start with n equals 0. We'll go from -1 open to 2. And so you think, well, okay, let's sacrifice that one. Knock that out. Knock it out. Okay. Then let's take, so suppose we drop that. Then let's say n equals 1. That one will go from 0, right, open, to 2 open. Well, okay. Maybe we should draw this. What do you think? I think it's much better if we draw it on the board here. It's a little bit subtle when we're dealing with these opens and so on, and maybe we shouldn't spend all that much time with one, but authentically engaging with these is not bad. Okay, now I am tempted to erase This is like prime real estate. If I move this over here, is this almost as good?
Yep. That's fine.
Is that okay? Okay. Okay, so let's just say, okay, so we have this kind of interval here closed to include this, and this is -1, right? And this is 1 all the way here, and it just keeps it going. And then we have these intervals that are open, like this one here. Maybe I'll draw this in the Egypt pen, right? The pay in pen. Like that, right? From -1 to 2, right?
Yes.
Payite pen. Yeah. Okay.
From 1 to.
And then we have another one from, so the next one up would be tempted to do it slightly at a higher level or something, from like 0 to 3. Okay, so this is 1, 2, 3. Yeah. And then we have another like from here, right, to like there, right? And maybe just to continue this would be like -2, and it would go to like 1. So is that right?
Yeah.
Okay. 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 So that if we knocked even one out, what would happen? So suppose we knocked every other one out. Well, every other one is not going to be a finite cover, right? So the question here is really whether there's a finite subcover, right? It's not whether there's a subcover. The question is whether there's a finite subcover. And maybe I didn't need to draw this. My neurons weren't firing properly. I was thinking the question is whether there's a subcover that still covers it, and then you knock every other one out. The real question is whether there's a finite subcover, and for any finite subset, you're going to leave some set of the space out, right? You're going to leave some big honking gaps out. I mean, you're going to only be able to cover so many things. You're going to leave out these big gaps of size 3, right? Well, not necessarily 3, but you're going to leave out these big gaps. There's just no way you're going to cover the whole thing with a finite set. Okay. Yeah, that was kind of hand-weaving, but I think we agree that like there's no way you're going to cover this infinite line with something that is so, it's of such finite extent, right? This whole thing is a finite extent. These pieces are a finite extent. You're never going to cover an infinite line with a finite set of things of finite extent. Okay. How about this one here? S equals 0 to 1. We're trying to cover 0 to 1. Do you agree that this covers 0 to 1? If like 1/n1 as n gets larger and larger, you get arbitrarily close to 0, right? You already open to the side, so it's but there's no finite subcover. What would happen if we tried to do a finite subcover? Well,
We picked an arbitrary n to be the last element.
exactly.
1/n+1.
Precisely. You just say, okay, well, tell me your maximum n that you use. With any finite subcover, you got to have maximum n. And therefore, all the points between less than 1 over that n will be left, in fact, 1 over n itself, and all points left of it will be uncovered. And the same argument could have been done here. Tell me your maximum or tell me your minimum n, and I'll tell you large amounts of the space that are right. Okay. Now then there was a discussion of compact sets, and this was actually, it wasn't a discussion, it was a remark that I found intriguing, and I went and looked into compact sets. So compact sets, all the basic idea here is these are sets for which every open cover, okay, has a finite subcover. That's kind of cool. That's kind of cool. Every open cover has a finite subcover. That actually takes some thinking, right? Because like you may be covering it with very fine-grained things, but there's guaranteed to be a finite subcover, and that will still cover this set for it to be compact. And Rosiak says observes that it constitutes a very special topological property. I will say that it turns out certainly in the usual topology, every closed and bounded set, bounded meaning, I think there's, I'd have to check the different, but I thought it was it's covered by a finite number of these things, although I thought that was finite subcover. Maybe it's covered by a finite number of balls or something. In any case, closed and bounded things are every one of those. Excuse me. I think it's every one of those is guaranteed to be have a finite subcover. To be compact rather. No, every compact thing. No, that's right. That's right. I think that's right. Every one of those is compact. There may be some compact things which may not be of that form. I'm not sure. In any case, these are some pretty nifty concepts. For finite sets, everything's compact. They all have a finite subcover. Any finite set that has a cover has a finite subcover because the cover itself is finite. You don't need an infinite cover for a finite number of things. Remember, infinite is judged in terms of the number of things in the cover, the number of sets in the cover. Okay. So this brings us to the notion of, so we've been talking about subcovers where really we're not focused on what the size of the sets are within the cover or subcover. We're focused on the collection of sets of the subcover being a subset of the collection of sets of the cover, right? Remember that? Like we have these two in the cover, and these are the subsets of this, the subset of this collection that are in the subcover, right? It's not that these are somehow finer granularity than these. No, they're the same ones. Or for many finite covers, subcovers. What distinguishes them? This is a subset of this. Okay. Refinement deals with, as I understand it, it deals with this notion of like how small, how fine-grained are those sets themselves? How fine-grained are these sets? How do they compare here compared to there for the refinement? So here we have a subset S, and we have cover U and V. And the idea is that V refines U. If for every, so remember, this is U and V are covers. So they're a collection of sets, right? They're a collection of sets that collectively cover S, right? Subset. We good with that? These are collection of sets. So we say V refines U. If for every one of those sets in that cover V, say V finds U. For every one in V, there's a U in U such that V is smaller than or is included in U. It could be equal, but it's included in U. It's no coarser than U. If for every one of those in our V, every one of these sets, there's a thing in the cover of U that's just as coarse or more coarse, then we say V refines U. And of course, we might say, well, if U's are really coarse compared to V's, it's going to be saying, well, V for every V, it's no bigger than any U. But then it's no bigger than what we see in the U's, right? There's at least one of these sets from U in the cover for U, such that V is smaller than it. Okay. So this is dealing with the granularity of those sets. And Rosiak observes for an open subset U and a trivial cover like this form, right? It's cover for U. Every cover of U will be a refinement of that trivial cover. Why do I say that? Well, look, every cover of U has subsets in it, right? There's subsets of U, every cover of it, or including some, or not necessarily subsets of U. U is in some space X, let's say. And the cover of U will have subsets of X that collectively cover U. And here we're not talking about a broader X, right? We're talking about subsets of U. So there are various subsets of U, and each of them is going to be a subset of U here, right? I mean, by definition, in the cover of U, we're going to have subsets of U here. As I think what's meant here, we're going to have subsets of U, and each of them is therefore, for Forte, is going to be a subset of U here. So U is the coarsest one. If we have a V with lots of smaller ones, each of them is a subset of U. That satisfies this notion that V is a refinement of this one. Does that make sense? Are we okay with that? Okay, so maybe you tell me, let's go back to our set here. So I was a little bit prescient, but I wanted to erase this. Thought it might be an asset. Here we go. And I'll turn off this. Can we see this? Can we see this? Okay. So which of these, if we say, so here's our trivial cover, right? Maybe I'll use the KI. K area. So this will be, this is the trivial cover, right? Which of these is a refinement of this cover? Refinement.
Put in all of them?
All of them, I think. That's all of
This is, that's right, and that's exactly what this says. Yeah. Okay, so all of these are refinement. This is what this says, because like for everyone, how do we know they're refinements? Well, for any one of these, we take the set and we say, is it a subset of at least one of these, right? We're asking, okay, is it a subset of at least one of these? And yes, this is a subset of at least one of these. This is a subset of at least one of these. This is a subset. Yeah, right? Even this is a subset. Yeah. So all these are refinement of the trivial cover. That's not as interesting. What would be more interesting is if we called these, maybe we call it 1, 2, 3, 4, 5. There's actually an interesting relation here, right? Or we could divide this up into, I'm not doing it well, right? We could do it something like that, and it'd be kind of cool. I've been playing a little bit. I was exploring last night. FinRel and CatLab. So there's FinSet, where you have the category of sets and functions, right? Like the objects are sets and morphisms are functions. And then there's FinRel, where the objects are sets and the morphisms are relations. And actually, it turns out it's a 2 category, which is pretty fun. But in any case, you can build relations between things. It compose relations, which is pretty nifty. Anyway, we could ask, like, is 1 a is 1? So call this V and call this U. Should really know how to like write it fancy. Okay, I need Jeff as a consultant. I don't know. Like,
I don't want to.
that's right. That's right. No wonder I didn't do so well in pen. What's that? Yeah, I know. It looks like, well, yeah, that's the problem. Yeah. I'll add a curly there. Gamma doesn't have that curly. Okay. So we could ask, like, is 1 a subcover of 1? And like, is the diagonal, what is the diagonal going to be here? True, right? Yeah. So I'll put a check mark. It's going to be true, because for every one of these, there's going to be at least one in the other that it's part of, well, itself, right? Like, so identity, yeah. Okay, how about 1 compared with 2? For every one of these, there's...
Except some of those aren't covers, though.
Sorry? Oh, that's right. Oh, gosh, yes. These aren't covers. These aren't... I was asking if they are covers. Yes, quite right. This was a cover, this was a cover, this was a cover, this was not a cover. So let's let's what do I need?
Add DE, I guess.
DE.
Yeah.
Okay. Good. Okay. So is 1 a refinement of 2? No. Because like this is not a subset of any of these, right? This is not a subset of any of these. This is not a subset of any of these.
Oh,
so,
camera might need to be rotated a little bit up.
up? Okay. Yeah. Thanks. Does it need to be shifted back to get the
Maybe, yeah.
the view? Okay. Is 1 within 3? No. 1 and 4. What is 1 and 4?
Yeah.
1 and 4? 1 to 4? Yeah, because every one of these is a subset of that, right? 1 to 5? Yeah. Yes. 2 is 2 a is 2 a refinement of 1? No. So this is a subset of that. This is a subset of that. This is not a subset of any of them. No. Is 2 a subset of 3? No. Is 2 a subset of 4? Yes. Is 2 a subset of 5? Yeah. Okay. I think you could fill this out more, but it's kind of interesting. Is this going to be symmetric? No, it's not. Right. U being a refinement of V being a refinement of U is definitely not the same thing as U being a refinement of V. The only thing that's I'm hazarding a guess that if U is a refinement of V and V is a refinement of U, then no, that's not true. They don't have to be the same, right? Like this is a refinement of this. This is a refinement of this, but they don't have to be the same. Okay, so that's kind of cool. We can have this kind of relation of what's a refinement of what. But I think you get the sense that, well, let me ask this. If we put more up here, if I put another 10 up here, is there one of these that's always going to be guaranteed to be a refinement of the others?
3.
3, because it's the finest grained one. Well, no matter what I put up here, this is guaranteed to be a. There ain't no cover more refinements. There ain't no cover with finer granularity pieces, right? That's kind of fun. That's kind of fun. Refinement is, I mean, this sounds a little bit ethereal or abstract, but I will say, like, when you're dealing with topologies of like ways of describing things, if these were age groups, and we're talking about, for our sheaf, reasoning about the number of infections per week for different age groups, there's going to be a certain topology associated with breaking out each age group. That is, distinguishing each age group as an open set that is going to be the finest one, right? It's going to be at least as fine as anything else. And it really matters. Like we care. Like, oh, that's really fine grained data. Like this helps us recognize it. Okay, I'm going to ask another question here. So it hasn't been that long. I think it was this week. Maybe it was last week, but so it was the end of last week. That we were first talking about the definitions of a topology, right? With open sets. Remember this? This is old hat to you now, right? But let me ask this. Is there anything in here? So you recall there are two. So if we have a topology on set X, there are two sets that are always part of that topology. What are they? Empty and total, right? Okay. Other than the total set, the set X itself, are the other elements of the topology, if there are others, like for the indiscrete topology, there aren't any others, right? Sometimes called the chaotic topology, right? But if there are other sets besides X and empty set, are they guaranteed to have a union equal to X?
Colopens.
Sorry?
Colopens. Colopen subsets.
Colopen? Sorry. Clopen.
Colopen. Sorry. Yeah.
Clopen
Yeah.
subsets. Okay. Things that are closed and open. Yeah, I'm even talking about something closed and open. Yeah, Clopen subsets are an interesting. Those are interesting ones, and there we have their relation to their complement. Remember that? A closed set is one whose complement is open. Remember that? Like we can take its complement. But here I'm actually asking something more basic. I'm actually asking if we have a topology whose, other than X itself, are the other sets in it, if there are other sets, are they guaranteed to cover X? No. In fact, we went and we saw some examples here. Do you remember here we went through this? Was this a valid topology? 0, 1, and 1, 2, 3, 4. Did that abide by the axioms for the topology? It certainly did, right? Right. The full set is in it, the empty set is in it, and all other sets, there are other sets such that they're closed under arbitrary union, right? The union of this and anything else, including itself, is in it. And the intersection of it with a finite intersection with a finite number, well, it's only a finite number here, is in it. So this was a topology. Does this cover this? No. Is this a topology? Yeah. Does it cover this? No. Right? Here do they cover it here? Is this a topology? No. Right? Like 2, 3 is not in it. Right? Remember, it has to be closed under union. Is this closed under union? Oh, arbitrary union. Is this closed under union? No. Is this a topology? Yeah, this is a topology, right? It's closed under union. It's closed under intersection. It is the full set. Yeah, unless I'm missing something, right? This is a topology, I think we had said. Do the sets here, other than this, collectively cover the entire set? No. 1 and 1, 2, and 1, 2, 3. They kind of creep towards it, but they don't cover 4, for example. So covering is not something which springs out of like these don't automatically, the subsets here that are the open sets don't automatically, if you exclude X, it doesn't automatically cover X, right? We will be bringing in this notion of being closed and covering things. In some of our needs. Okay. That's kind of a aside here. Okay. Okay, so kind of talked about these, yes. Okay, so there's, as you might have guessed, when we came to refinement, there's a category living here. The objects are covers of a specific set U. So you can think of them as collections of sets that cover you. Why don't we take 30 and you? Is that a comfortable notion? Covers, right? Talk about it. Could be infinite covers. No one's saying that they have to be finite, right? The set U could remember the set U is fixed, right? It's constant here. Like this is a category for a particular U, right? And U could be infinite. It could be uncountably infinite, right? Could be reals. So we have covers. The objects are covers, different covers for it. And the morphisms, there's a morphism from V to U, from cover V to cover U, if V refines U in this node. So let's do a sanity check. What are the identities? What's the meaning of an identity? A morphism from V to itself. That's identity. What would that mean? Yeah, it refines itself, right? And we said that before. Remember, that's the diagonal. Do you remember that? That's why we had check marks on the diagonal. If you have V that refines U, and U refines T, does V refine T? Does that make sense? Think about it, because remember how refinement is defined. It's this subset, right? So if there's at least one up there, and then that one can be found in another, in T, then it follows a sense like informally, I don't take this too seriously, but the subset is, you can compose subset, right? If X is a subset of Y and Y is a subset of Z, then it follows that X is a subset of Z, right? All right. Are we okay with this? So this is a kind of cool category. That's a pretty darn nifty category. You got to say that's pretty cool. Bet you didn't see that coming. So that's pretty nice. You could imagine capturing that in it, right? These ones that we had there, right? And really where we put a check mark in that table would indicate when there's a morphism from V to U, right? V is the rows, U is the columns, and where there's a morphism from V to U, right? Let me ask this. Is this a thin category? Is there really sensibly only one morphism from V to U? Or can you have multiple morphisms from V to U? Well, it's really binary. It says if cover V refines U. So it really is a thin category. It's just one. Remember other thin categories we've seen? Do you remember that? Do you remember, like, probably I have some, maybe I have some back here. Oh, no, I don't have some back here. Sorry. But remember, we've had other thin categories. What's another thin category we had? Well, does M divide N, right? Is M less than or equal to M? Is subset S a subset? Is set S a subset of T? Remember that? This is just like that. It's a thin category. Is it a pre-order? Is this a thin category where it's acyclic? I'll ask that. Are there cycles here? I think it's one way. I think it is a pre-order. I think it's. In other words, I don't think you're ever going to have a cycle where like X is a refinement of Y, and Y is a refinement of X without X and Y being the same. Could you? Could you? Maybe. Could you have that? That's kind of interesting. Every set in the cover for X has at least one thing in the cover for Y for which it's a subset, and vice versa. I guess you could, right? So it's not actually pre-order. I think, for example, if you had X itself, if you had the total set and then another set, and each of them figured the total set, but a different set, then for each one, they'd be a refinement. They'd say, well, I'm a refinement of the other, but they, you know what they are? They're isomorphic with respect to this. I think they're actually play an isomorphic role because there's morphisms in each way, such that if you compose the morphisms, it's equivalent to morphism from X to itself. Maybe. Anyway, I'm not going to speculate, but I'd like to think about that more. Okay, so sheaves. We're coming up really quickly on sheaves. Sheaves are going to be next week onward. Okay, so let's talk about sheaves. For a sheaf, the sheaf axioms, as Daniel Rosiak says, have to hold for any cover, for all covers. The concept of sheaf, as he says, combines the notion of a pre-sheaf and the notion of a cover. If we, in the notion of it's a cover and a topology. I mean, it's I don't know why I said topology, including cover. Yeah. So it's really, we have a topology imposed here. If we have a sheaf over cover V, then it is a sheaf for any cover that V refines. Should be. So this allows us to verify a sheaf like the most fine grained thing. And something that's really cool here and very practical, very, very significant, and really is highly relevant for computational use of categories, like that are central to our work, is this notion here. So if we have, let's suppose we have some big awful space. Well, maybe it's not an awful space. Maybe it's 3 space. Maybe it's 2 space. Maybe it's geographical space. And we have some topology in it using, say, the usual topology, right? We have these different open sets within this topology. It should be comfortable notion, right? We have this space, and we have open sets that satisfy all the rules of topology. And so they're closed under intersection, they're closed under union, under arbitrary union and finite intersection, and the whole set is in it, and the empty set is in it. Okay. So it's a topology, and maybe it's the topology, the usual topology. And the idea is we can take the nerve of an open cover of this. Okay, so the idea is that we have an open cover for this, and for our set here. And maybe it's of these open sets. We take what's called the nerve. And what that does is this is a really important idea. We're going to see this a lot. So each of the open sets so you'll see that we have these balls here, and then we have their intersections, and then we have their we have two-way intersections like these. You see this, and three-way intersections like this, right? This is an open cover shown. This is our open cover U. You may recognize it, right? These covers. This is our open cover for our set associated with our topology. Okay, so maybe this is in physical space. This is some region of one sensor picks up. This is a region of another. Maybe this is a geographical area. This is a geographical area. This is a geographical area. Okay. There's going to be some areas which are only covered by one. There's going to be some areas which are pairwise in the intersection, like between the sort of tan and the teal, the tan and the gray, right? Or the teal and the gray. Here are these two-way, and here are these three-way. And we turn this into a simplicial complex, where each of these regions which have just a single point associated with, like the tan one, or the gray one, or the teal one, that's where there's no intersection. Each of those becomes a vertex, a zero simplex. The pairwise intersections become one simplices, so they become the edges, right? Like this region here is this edge from this set to this set, okay? So they have some intersection in this open cover of this space. Remember, an open cover of a topology can be some regions, right? Remember we drew it up last time. We had like a region there was an overlap. Remember that when we were demonstrating that there's an overlap between these regions. We reasoned about that overlap. This is like an overlap between regions picked up, right? This is our open set here. We're covering this space with these open sets. This is intersection between them. That becomes this edge. There's an edge for the intersection between the teal and the gray right there. There's an intersection between the teal and the gray and the teal and the tan there. Okay. And then where all three intersect, you get the two simplex, right? It is bordered by these two-way intersections, but it's also bordered by the, just these open sets itself, right? These open sets, these intersections are there. Just there's some regions there that don't have it, and so we have those in these zero simplices, the vertices. Now, this is associated, moreover, with the category. So the objects here are the ordered sets we talked about a couple days ago, associated with these open sets. You may remember when we talked about those. Remember these things here? Remember that? This is Friday. We talked about, like, there is a here for like V1, there's I variously wrote it as with brackets or square brackets to connote that it was ordered here. It's an ordered set V1 itself for V1, V2 itself for V3 or in V3. Remember this one here. Do you remember what was the ordered set associated with this by itself? This two simplex, what was the ordered set? V4, V5, V6. Yeah, it's this one right here. And pairwise, V4, V7, for example, here, right? Okay, so that same notion appears here. These are those sets. Sorry. These are those sets. So this is a set here for so this would be for AB. This would be for just like A, B, C. This will be for all of A, B, C. So this is This is the set associated with an edge. So this is edge. Maybe we'll start with the vertices. So this is vertex tan. This is vertex teal. This is, which came from that region earlier. This is vertex gray. This is edge. I'm not even going to say what is that color. I'm not sure what that color is. Greenish, green, turquoise kind of. I don't know.
Because I have difficulties in recognizing.
Yeah. So whatever color that is, it's this one. This one is whatever color this is. This one is whatever color this is. And then this one is for this simplex here. Right? That's why it's the same color. So these are for the vertices. And you'll notice the morphisms, there's a morphism, this is an object, right? There's an object representing this set. And there's a morphism from X to Y, object X to object Y, like here from an edge to a vertex, if the set associated with the target, the vertex, is a subset of it for this. So this might be, for example, X comma Y, and this might be, I'm sorry, I'll use it because we have Y and X here. I'll say this is A comma B, and this would be like A. So the target of the morphism is a subset of the set. The set for the target of the morphism is a subset of it, the set for the source. So this is the so-called nerve of this, and this will play an absolutely central role for many sheaves. This construction. This will give us our simplicial complex associated with the sheaf. This will encode our topology, and this will be reasoning about things in this category, and reasoning about the behavior of the sheaf. The data over this and the data over this, say this point, tan and teal, they have to agree, and that's dictated, they have to be consistent at some level, and that's dictated by what's going on along that edge. So what's depicted along the edge and what's depicted in each of the vertices here, really we're dealing with this axis from this topology. They have to be consistent. They have to play nicely. So if this is data about the sum of cases over these two regions, we say there are 13 cases over this region. This could be 6 and this would be 7. That would be consistent. But if this were 8 and this were 15, that would not be consistent with this. So the sheaf will be keeping track of behavior over these spaces. It'll have data for each of these spaces, and we'll be reasoning in this category about this, the consistency of the data. Okay, and the optimist category. Now, it turns out that the reason this is so useful is a nerve theorem of Leray and Borsuk, which basically says that when you do this, it preserves properties of the topological space. And that is true in certain cases. It's not true, for example, in this case. And then there's the nerve lemma does not apply to certain things, but it does in others. And it has to do with this notion of contractibility, which is more than my pay grade right now. So I don't grok this. This is a non-contractible space, but this is a contractible space. But this is a standard thing you'll do if you have like a continuous space, like again for sensors or for radar systems and Robinson's work or whatever. You turn it into a simplicial complex, and you turn it into a category, and then we're going to reason about functors from this into a space of behavior, which associates each object with some data received for that object. Okay. So that's where we are going in next week. So this is this notion of a nerve of an open cover. And it turns out there's a nerve of a category too. So the nerve of that category, can you believe it? Okay, that's all we have time for.